Good morning, everyone. Day 3. We went through day 1 of Frontiers, where we had Tomasz and I have a little fireside chat on the state of Ethereum, crypto, and where we're going. Yesterday, we had a pretty intense day where we had some talks focused on applications. We had an insane demo from Guillermo Adversel about the future of coding with AI and with Porto. And today, the day is a bit different. Today, the day is not focused on applications. It's focused on hardcore back-end Rust engineering. So these talks that you're going to hear about today, they're very focused on distributed systems, high performance. They're not for the faint of heart. I think they're not talks that you can lightly follow. I think you really need to lock in for these talks and pay close attention. We've done so much work to optimize our code, and we're going to start the day with Alexey and Dan from the Reth team, who will talk to us about optimizations that we did to the Reth code base since last year, which have 5x'd the performance of the node since then. And we're just getting started. So give it up for Alexey and Dan.
All right. I'm Dan. This is Alexey. We're both on the Reth team, and we're going to be talking about all of the optimizations we did about the past year since last Frontiers to 5x Reth's performance. But first, we're going to talk about why do we even need performance? Why is it important to optimize clients? Why do we spend a year doing this? So we're going to see what kind of motivates all this. One reason is growing demand, right? There are more and more people using the chain, the world's changing, and for that, we need the capacity to actually support all of these new users. The next is use cases. There are a lot of new use cases or old use cases that require high throughput, low latency, like exchanges, payments, and we need to support these use cases. If the client can't support it, then these use cases don't exist. The final thing is decentralization. If you're running a node and you have a validator, it's run on some box for a few years, the layer 1 is going to start to scale. And so you need to make sure that box can still support the growing capacity of the chain. Layer 2s are also scaling. So for example, Base has set some pretty ambitious scaling targets from 50 megagas per second to 250 megagas per second. If Reth wasn't able to handle this load, then it wouldn't be possible to actually achieve this. So we also need to make sure our L2 software is performant as well. And on the L1, because we're scaling the L1, we have set up these great end-to-end load tests and really networks that will allow us to test, is the chain going to continue succeeding when we bump the gas lot? Will it keep working when we make the state size very large? Really testing these kind of degenerate cases that might occur if you just start bumping gas limits. So these can sort of serve as a preventative measure to make sure that we see what the bottlenecks are before they actually happen in production. Next, we're going to talk about how we as a team actually try to improve the client performance. First, general principles for improving the client. There are a few optimizations we're going to talk about later today. But they've kind of taught us a few things on generally what's important when you're trying to design your client architecture. And these 3 things are, one is pipelining. When you have a bunch of steps in a process, you only want to wait for something if it's absolutely required. You never want to wait for no reason or because it's maybe logically simpler to see in the code. you want to make sure that you do next steps of the process if you can do them. Next thing is you need to make sure that you're actually using the whole machine, using all of the threads of your machine, using as much of your resources as possible, minimizing I/O. Not everybody has like a super fast SSD, but even if you do have a fast SSD, if you minimize I/O, everything will just happen much, much faster. The final thing is executing optimistically. These are sort of applying heuristics to make the happy path much, much faster. So if you can do something and then keep going as if some statement were true, and that statement's true like 90% of the time, and that makes your code faster, you should do that. How we actually optimize the client goes a lot deeper in terms of the tools that we use. So we have to profile a lot to make sure that the code is actually fast. It's a very, very complex piece of software, and we use this profiler called Samply to generate flame graphs. This allows you to look through like the whole pipeline of some process that you're doing or some benchmark that you're running. So you can see every single thread, you can see it over time, you can filter things. It's a really good tool for understanding what's happening in the program. And if you don't know what's happening in the client, then you don't know how to optimize it. The next is that we benchmark things. We have to benchmark a lot. We have to do this with really accurate data. If you don't have accurate data, then the optimizations you're making aren't actually going to work in the real world. So we have this tool called Reth Bench, Reth Bench Compare, which allow us to take real-world data and throw them at the node so that we can get these accurate benchmarks and see, OK, did this change that we made actually make it faster? And it also allows us to collect profiles and analyze the node very, very easily. So before we dive into the optimizations, let's show basically what happened in the past year. So last frontiers, we were about like 40, 50 megagas per second for client validation. So when you process a new block, it needs to validate it. That's kind of how we're measuring that. And you can see that today we're at like 400 megagas per second. We think we can go higher, but it's a really, really good improvement since last year. So now we're going to explain what are we actually optimizing, which process, and what changed. So the lifecycle of a block or block validation is the thing that we've been trying to optimize for the past year. And it has a few steps. So the block usually comes in, it enters the node, and we need to perform a bunch of different validations. One of the validations is the pre-execution validation. These are things like validating signatures. The next thing is the EVM. You need to actually execute all of these transactions. Next, you need to do post-transaction validations, which are calculating the state root and the receipts root and a few other things. And then finally, you need to return the response, so whether or not the block was valid. So this is the process that we are trying to optimize. And the two things that are the most heavy in the node are the state root calculation and the EVM. These are by far the most intensive things. So we're going to focus on things related to that for the rest of the talk. Last year, we had an architecture that looked kind of like this, where basically you would have these pre-execution validations, and then you have like a whole single-threaded process for EVM, for state root, for post-execution validations, and you do storage root calculation on some other threads. This is very, very serial. We took a look at this and said, OK, this is not very good. So now we're going to show you what it looks like today. And it's much, much better. We're using a lot more of the computer. So we have most of these things happen in parallel now. along with some additional things that make the node faster, like pre-warming. So from my point of view, this looks a lot better than last year. So this is where you have to lock in, as Giorgio said, because the next things we're going to talk about are the actual details of the optimizations that we did. So the first optimization I'm going to talk about is caching and pre-warming. So when you're executing a block, this will make a bunch of operations related to disk. So you'll go and fetch some data, like an account or storage slot, and it will take some time for the disk to respond with the answer. It'll do this a bunch of times throughout execution, and you have to wait for it every single time. This is very slow. We want to speed this up. So as you can see, most of the time is just waiting if you're doing kind of the naive EVM execution. So what we want to do is we want to cache stuff. We want to cache as many things as possible. And so we introduce cache. If you cache things, the disk operations can be kept around for longer, and you can retrieve them if you have them in the cache. But the problem is that if you just introduce a cache when you're executing, it's not actually going to do anything most of the time, because you're probably fetching lots of different accounts. And if you're fetching an account that's not in the cache, well, then you're kind of out of luck. So how do we actually warm up these caches to make the performance much, much better? And we do this with something called pre-warming. So that's that other box, which you didn't see from last year's architecture. So what pre-warming does is it executes every single transaction optimistically to try to warm up these caches, and then it throws away the results. So even if the transaction fails, it doesn't matter. This gave us about 30% improvement on machines with slower disks, so this was very, very nice. And here's some graphs on our latency. So when I mentioned block validation, we want lower is better. So the baseline was about 150 or so, and we brought it down to like 50-ish afterwards. So the way that it works is we have our regular execution thread. It's executing transactions. And then we spawn a whole bunch of transactions in parallel. And what this does is they will try to access most of the accounts that these sequential transactions will access, and it will load them up in the cache. These won't be perfect. It'll also load some stuff that won't be loaded during regular execution. But it turns out this is a very, very effective optimization, because most of the time it just works. Now, pass it over to Alexey.
All right. Thanks, Dan. So I will talk about two optimizations that we did in the stage root calculation part of the pipeline. First one is the sparse trie. So the main idea is that how do you calculate stage root? You execute your transactions, you gather the state updates, you update the trie, you calculate the hashes, and then you get the root hash. What if instead you stream all updates as they happen in the trie? You keep in-memory structure that has a sparse version of the trie, so it's not the full 150 gigabytes MPT. It's just the nodes that you actually updated. And you can also hash the sub-tries in parallel. So you can hash in parallel the storage tries. You can hash in parallel the sub-tries of the stage root, sorry, the state trie, by basically splitting the big trie into, say, 256 smaller sub-tries. And this allows us also to utilize the I/O better. Generally, we get 40% improvements or even more on all machines with this change. And we had this amazing comment from a Reth BSC user who had the latency decreased from 120 milliseconds to 40 milliseconds, so 3x just from this change. This is a parallel sparse trie, so updating the subtries in parallel. And the chart looks like this. As you can see, we were at about 150 milliseconds, and it jumped to down to we were at 200, jumped to 100. So 2x improvement, and as you can see, there is spike here, and there are generally spikes. This is most likely due to Zen transactions. Those who know what is Zen know that they basically spawn a lot of storage slots, and this can mess with the stage root calculation. But we also fixed this recently, and this shouldn't be an issue anymore. So how did it work before the sparse trie? As Dan said, you have the EVM. It's sequential. You cannot do anything about it, but you can do some pre-warming. But then we actually execute the transactions one by one. You execute the transactions. You gather the state updates. You fetch all the trie nodes from the disk. You do some I/O, and then you fetch. And then you calculate the root in memory. With the sparse trie, what you can do is you can have two main threads. So the thread 6 here, the thread 5 is the EVM, and the thread 1 is the sparse trie. You start the execution for the transaction 1. When it finishes, you can fetch the state updates from disk. Not just the state updates, the trie nodes that were related to the state updates. So your transaction updates an account A, and it updates the storage slot for this account. What you do, you fetch a trie nodes, all the trie nodes in the path to this account in the MPT, and you also fetch all the nodes in the storage trie in the path to this storage slot. You do not wait for it to finish. So it happens on a separate thread. You just keep going with your EVM. You execute the transaction 2. Same happens to the transaction 2. You go to the disk, and you fetch it on another thread. So we try to utilize as much threads as possible. We try to maximize the I/O that we do in parallel. And when we actually get the trie nodes from the disk, we can update the in-memory trie. So as I said, this is not the full trie, not 150 gigabytes trie in memory. This is just the nodes that were in the path to the updated leaf. And basically, it takes very little memory, and you can store it in your RAM. Same happens to the transaction 2 and its updates. And as you can see, we can actually proceed to the next step of updating the hashes in a trie. So what you did, you updated the trie and the leaf values, but the hashes are still old. So the root hash is now outdated. What you do, you update the hashes of the whole trie, and in the same time, you keep executing. So the transaction 3 does the same trie node fetching, updates the trie, and that's it. That is our block. And what we do next, we calculate the root. You can notice that we can make some redundant work, because we update the hashes twice. And what if, for example, you update the same account twice in 2 different transactions, so you keep doing the same update multiple times? That's OK, because you do it in parallel, and our benchmarks show that it's actually better to do some redundant work on a separate thread than do it all without any redundant work in one thread. Next thing that's related to the stage root are nibbles. So we store trie nodes keyed by a path to these nodes. And the path can be represented as a sequence of hexadecimal characters from 0 to F. Each character is 4 bits, so it's not a full byte. 1 byte is 8 bits, and a nibble is half of a byte. You need to have this data structure because a sequence of nibbles can be odd, so it's not a full byte sequence. And what we did, we basically decided to store them in a more compact way, and also use better algorithms for the comparisons, for stuff like calculating the prefixes and slices. And in the future, we can also do a very interesting thing. In LLVM, there is a native I256 type. That's obviously not native to your machine because machine is probably 64-bit. But it can do some interesting optimizations that we cannot do in Rust. But it's not possible today because of the compiler. So the compiler kind of doesn't allow us to do it yet. This gave us a 20% improvement on all machines. That was kind of surprising to me, because it's just a small change. You store, like, instead of 64 bytes, 32 bytes, and you do faster comparisons. But there is so many of them that you actually gain a 20% improvement. And it went down from like 85 to 65 milliseconds. Very good, very nice. So let's go through an example. The trie on the left, we have it in memory, and what we want to do with it is to insert a new leaf. This leaf is at the path 17813, and it has an odd length. What you do, you walk basically node by node, and you build your path. You build it all the way to the new leaf node, and then you add the leaf node in the trie. So there was no leaf node, now there is. So we have this path, and we need to store it somehow. We have a crate for it, Nibbles. Has a lot of downloads. We use it for all the trie-related things. And we store it as 5 bytes, because the high nibble is 0, and the low nibble is set. What we can do instead, we can store them as 3 bytes. So we compact the nibbles into bytes, and the low nibble of the last byte now is set to 0. We need to distinguish, what is it, 3, 0, or just 3? For this, we store the length. Speeding up because we are like out of time. We have the length either 6 or 5. If it's 5, it's actually 3. If it's 6, it's 3, 0. The 3 key optimizations, if you sum it up, that we made to Reth since 2024 were starting with the bottom. So we optimize the data structures that power the execution, the stage roots, in this case, nibbles. They power the trie calculation. You optimize the EVM, you do less I/O, and you optimize the stage root calculation. So what's next? We have some ideas. Trie database is a very interesting thing. Next talk will be about it from Brian. And basically, you divide where you store your data, not just in one database, but in multiple databases. Our goal is to minimize the non-EVM overhead, so when you increase the gas limit, you should just expect longer EVM execution, but no additional like stage root overhead or I/O overhead. And another very cool thing that I'm very excited about is the block level access list. Basically, it's a path to the parallel EVM on mainnet and on L2s. If it gets in Amsterdam, we'll get it. So talk to your local core dev and get it in. That's it. Thank you very much. Questions?
Hi. In the sparse Merkle tree idea, because you are parallelizing all the trie prefetches for every transaction, how do you handle like transactions accessing same accounts? So like if, let's say, the prefetch of transaction 2 completed before the prefetch of transaction 1, then your in-memory Merkle tree is constructed wrongly. So like, how do you handle that?
Yeah, that's a good observation. Thanks. So we fetch the data in parallel, but we apply it sequentially. So there is a queue, and you apply it only in the order of transactions, because if you delete something and then you update it, it's not the same as doing it the other way around. Yeah.
Oh, there we go. First of all, awesome talk. Thanks for all your hard work, guys. One of the questions I wanted to ask was, you obviously have like a lot of parallelism going on inside Reth. Are you guys usually leaning more heavily on like shared mutable state with like mutexes and RW locks, or are you like spawning new threads that own data and like preferring the actor model for most of your parallel tasks?
Definitely second option. So we have a lot of Tokyo channels or just STD sync channels that we pass the data with. And we have standalone threads that do some work, and then they pass data further. So there is no locking, and it all works on just atomics. So there is minimal overhead.
How do you guys benchmark trie calculation with I/O latencies? Because right now we see the benchmark doesn't have that. Everything's loaded in memory.
Yeah, so Samply doesn't show any I/O because it's just a CPU profiler, and what you have basically like an empty space when I/O is in the progress. It's harder to measure. We basically identify on the profile these empty regions, and we see that this is just the I/O, and we try to minimize it. Usually you benchmark it via running the same blocks on main and on feature branch, and you compare if it got better in the latency. But it's harder to measure the actual I/O. For this, we, I think, have a Grafana dashboard for the system I/O, and we see how much data is read or written. Mostly read, yeah, because the written data is always the same. Does that answer the question?
You guys have a benchmark for the file right now. That one does not have any.
Oh, you mean the benchmark like
Yes.
cargo bench?
Yes, the bench.
OK, yeah. This doesn't measure the I/O. The cargo bench is only about the latency of the trie calculation. And the cargo bench also doesn't operate on a big state. And the I/O cost comes from having a big database. So cargo bench currently doesn't have it, but Reth bench and running on a real node takes this into account.
But do you guys plan to add that to the bench? For example, you can simulate some I/O latency and then put 1 millisecond here or 2 randomly to just act like you are reading from the disk.
We welcome the PRs.
We already have that. We'll send it to you.
Yeah, but yeah, that's a valid idea. We'll think about it, yeah.
Thank you for the great talk. My question is about the parallel pre-warming phase. You mentioned that you discard the results.
Mm-hmm.
I'm wondering if there's a reason for that, or if you plan to maybe use the results of transactions that don't have any state conflicts to
Right.
just apply it.
Yes. So right now we discard the results because it was like the easiest thing to implement as like the first time. We're currently experimenting with keeping the results and doing basically conflict resolution when you get to that transaction mid-block. So the idea is if you keep the results around, you keep around the state that it read, and then when you get to that transaction, you check, OK, is the state the same? So if the state was the same, nothing would have changed from the pre-warming version, and you just apply the result and keep going. You skip the execution. So yeah, it's a good idea, but we're currently experimenting with it. So yeah.
OK, I think that's the last question. Thank you so much.